Hello everyone, I'm Sanya Irfan and welcome to Module 2 of the Deep Learning series. Today we are covering something extremely important, linear algebra and ML basics. This module will help you understand the math behind neural networks in the simplest possible way. Let's move forward. Why linear algebra in deep learning? Such a great question. Deep learning is basically powered by matrix mathematics. So all the data we feed into neural network like images, text, embedding, audio is stored as vectors or matrices. Every forward pass and backward pass that the network performs happen using matrix multiplications. And GPUs are specially designed to accelerate these matrix operations. So without linear algebra, deep learning cannot exist. Scalars, vectors, matrices, and tensors. Let's start with the building block. A scalar is just one number. A vector is one-dimensional list of numbers. A matrix is two-dimensional grid of number. A tensor is a multi-dimensional version of matrix like 3D or 4D. In deep learning, a grayscale image is 2D matrix. A color scale image is a 3D tensor, and a batch image is a 4D tensor. Let's move forward. Vector operations. Vectors are important because they represent data, weight, and embeddings. Basic operations is addition and subtraction. It's done element by element. Scalar multiplication. Multiply every element by a single number. Dot products measure similarity between two vectors. Dot product is also used in attention mechanism inside transformers. Okay, here is matrix operations. Matrix operations are everywhere in neural network. We do matrix addition, matrix multiplication, transpose, use identity matrices. Matrix multiplication is especially important because it's the backbone of every neural network layer. Why matrix multiplications matter? This formula is the heart of the deep learning is output is equal to weight into input plus bias. Every neural network layer does these operations. The output then goes through an activation function. This process continues layer by layer until we get the final prediction. That's why matrix multiplication is so powerful. It's literally how neural network think. Next, which is activation functions. After computing the weighted sum, we apply an activation functions. Some commands are on our screen, which is sigmoid used in binary classification, ReLU, the most popular activation, tan similar to sigmoid but centered. Softmax used at the last layer of multi-class classification. Activation functions help the model learn non-linear pattern. It is very simple. Look, activation functions helps the model learn non-linear patterns. It's gradients, very interesting. Gradients are simply slopes. They tell us how much and in which direction we should update weights. If the gradient is large, the weight has a big effect on loss. And if it's small, it doesn't affect the loss much. Backpropagation used gradient to update every weight in the network so that the loss decreases. Next, is loss functions. The loss function tells the model how wrong it is, of course. So two important losses here mentioned is MSC, mean squared error, for regression, and cross entropy loss for classification. Training means reducing the loss. Next is optimization algorithms. So to minimize the loss, we use actually optimizers. Some important ones are on the screen. It is gradient descent, SGD, ADAM, learning rate. ADAM is the most commonly used today because it adapts the learning rate automatically. Underfitting versus overfitting. Underfitting happens when your model is too simple and cannot learn patterns, and overfitting is just opposite. It so happens when the model memorizes training data and doesn't generalize. Okay, deep learning model must find the right balance. It requires balance. Regularization techniques. Here some are mentioned. So listen. To avoid overfitting, we use regularization. Understand it like when we feel emotionally overwhelmed, we regulate our emotion. Exactly like this. Here is dropouts turn off random neurons during the training. Look, it's all the web of a neurons. So in dropouts, it drop out some of neuron. Okay. In L2 regularization, it's a penalized large way. Okay. Early stopping prevent overtraining. Like look, if it gets overtrained, so before it get overtrained, we just stopped. It's called early stopping. Batch normalization stabilize training. Look, as we understand in our first PPT that batch is like optimizing a simple of training data in loop. Okay, so what we do, like if there is a 70 batch, we decrease it in 65. Okay, these techniques help the model learn better and more reliably. Train validation test split, very important. This is a standard ML pipeline. Okay, train set used to learn weight. Okay, first we make it learn. Validation set is used to tune hyperparameters. So all these epoch, batch, and all these are hyperparameters. So test sets used only at the end for final evaluation. Okay, never train on your test set. Look, never train on your test set. ML workflow recap. This is a complete ML workflow, like we can see on screen. It's data, like prepare data, features, extract features, model, choose proper models as per your requirement, and then loss, define the loss functions, training, train the model, and evaluation, simply evaluate and deploy. Almost every project follows this pattern. So where linear algebra appears, you will see linear algebra in convolution operation, word embedding, and attention matrices, and backprop gradient. Look, understanding these modules helps you in every future concept, including CNNs, RNNs, and transformers. Okay, let's move. So in next module, inshallah, we will learn neural network and